and life load, I'll be also staying with the same model and continue on the portion. The key points, I kind of covered them briefly too, are DXF import for defining 3 different parts, and construction state, defining construction stage, how to set up, if you have used civil, you're probably familiar with these terms, structure, boundary, and load groups manually, and how to assign them to each stage to simulate the actual staging that's happening for you. I had a couple feedback that you're having difficult time hearing, not hearing anything. Can anyone provide a feedback if you hear well or not right now? Thank you so much. Thank you, everyone. Okay. And also connecting to the staging definition, how to define concrete time dependency for the compressive strength, shrink and shrinkage, creep and shrinkage, and pre-stressing in connection to staging 2, and how to do approximate load calculation as per AASHTO, and moving load, setting up the lane, vehicle, moving load case, and so on. For the moving load portion though, I plan to have another session that kind of covers it in depth. So today will be more like going over setting up and reviewing the result. And everything that I'll be going over today, you can actually find a detailed tutorial. I'm going to upload them all on our Midas website and send it to everyone who attend, and even for the ones that just registered too. So moving on to, prior to moving on to the manual portion, I'll quickly go over what are the different type of wizards for segmental structures. So for example, as you can see, when you come to the structure main menu, you can find different type of segmental wizards: incremental launching method, construction type, free cantilever method, and movable scaffolding system, and full shoring method, and so on. So for any type of segmental staging, you can actually find the wizard. And for those who are not familiar with our material database, not only on our website, but also when you go to our, once you install the program, go to Program Files and go to Midas folder and go to Midas Civil folder. You're going to find 2 important parts: tutorial and manual. And once you're going to, in the tutorial folder, you can find all different type of example models. And these wizards that I just mentioned, you can actually find example models within your program files. Free cantilever, incremental launching method. So for different type of wizard, you can actually find a specific tutorial for it. And that's the model, those are the model file, and you can go to the manual folder, go to the tutorials, and find actually a step-by-step thorough tutorial manual in this folder. And when you actually open them, these are actually really thorough. It can be very lengthy too, depending on what type of how you follow, you know. If you are more of a person who just kind of take out what you need exactly and move on, this may be a very lengthy and detailed tutorial. But basically, every detail you can find on this default tutorial manuals. So I was going to cover the wizard a little more, but I will cover the manual portion more heavily today. Okay, coming back to our the manual approach. As mentioned briefly in the beginning, I'm going to cover this first portion, defining a section with 3 different parts. So how I'm going to do, I'm going to use my DXF file that I actually drew in AutoCAD program, but you can actually draw in MicroStation too. As long as you save it in DXF format, you can bring it into Midas Civil. And I am going to go over some of the important things that you have to be cautious about, such as unit setting or tolerance setting. One of the most frequently asked questions by our users is whenever they try to import CAD into Midas Civil, settings such as units or tolerance, it's difficult for them to determine which way to go. So I'll try to focus on those parts. And also highlight some of the other parts that you have to pay attention to when using the CAD program. And generating composite sections with 3 different parts or 2 parts, and importing them to Midas Civil, and modeling a simple straight line girder model so that I can show you construction stage and the analysis result in very simple manners. So this is an overview of the 3-part section that I'm going to model. I'm just, for this portion, the first session, I'm only going to model just a straight line girder, but you can take a look at what are the overview information about the section, where I'm getting this information based on. So basically it's a 2 top girder structure. And for the negative support section, it actually has a plate. For the non-support regions, it doesn't have a plate. We pour the concrete straight onto the false board, but this is how it's done for the support regions. And this is what I'm going to show shortly using the CAD and section property calculator tool in Civil. And the staging that I'm going to demonstrate will be in this order. Part 1, just the top girder portion will be activated. In part 2, the plate cover will be placed on. And in part 3, I'm going to show how you can actually activate the deck portion, making all this fully composite. And then we'll go over the analysis output. You can actually go over the analysis output about each stage. So stage 3 and about part 1 and part 4 total for the composite, all 3 portions. And you can actually review parts by parts. And also over here, you notice that I'm actually reviewing for the final stage. But you can actually change which stage you want to review about and review for non-composite state and so on. Okay. So in this CAD program, I just drew one single section. As you can tell, it's the right side girder based on the drawing cross-section view that we reviewed. As you can tell, it's made of 1, 2, 3 portions. This is just a dimension line, so don't mind it. And a couple things to note when you try to import CAD to Civil is that they first need to be, if you actually drill with connected line, you actually need to explode all your lines first. So prior to importing them, just make sure that you explode them. And also a couple other things, a circle or arc cannot be imported directly to Civil. So if you are trying to import a curved line, you have to break them down into group of segments of straight lines. And also spline cannot be imported into the Civil. And the reason behind it is because FEA program runs with the basis of just a node and beam element or plate element or solid element. Spline or circle and arc are the concepts that are not existing in FEA program. So that's why there goes a little bit of background for the limitations. The reason why arc, spline, those type of non-linear CAD elements cannot be imported into Civil is because FEA program don't really have such element as its basis. FEA element runs based on node, beam element, which is straight, and also plate or solid element. And none of them are actually equivalent to circles, arcs, or splines. So regardless you have CAD program or MicroStation program, save them as a DXF format. So regardless what you have, as long as you save it into DXF format, I know MicroStation is more of a common CAD tool for our bridge engineers, but don't worry, as long as you save it into DXF, it's all good to go. So now what I'm going to do, I'm going to open a brand new file in Civil. And here, before we directly import it to Midas Civil, there's one more step to go through. It's called Section Property Calculator, right here. So you can find this tool under the Tool main menu, and then among many of the generator functions, you can actually spot the Section Property Calculator. Okay, and make sure to set the unit. The weight wouldn't matter because the CAD information don't have the weight with it, but the length will be very important. Make sure it is actually aligned with what you defined in the CAD program. And most likely, 99% of the time, it's going to be inch for our US engineers and millimeters for the Canadian engineers or any other area that are using SI unit. Okay. And tolerance, this is also a factor that can really affect your importing. So right now, my section is quite, it's not very sophisticated. It's just a bunch of lines. You can tell the dimension of the smallest line is, it's still a few inches. So having tolerance as one wouldn't really matter. But if your drawing is very sophisticated, if it's a very detailed connection member, you have to consider reducing the tolerance number. It's not always, I can't really say a standard, but then let's say when you import something and the drawing doesn't look right, and your CAD drawing is quite sophisticated, you have to, tolerance is something you can pay your attention to. So I set my tolerance as 1 as a general, and I go to import, and then I'm going to find AutoCAD DXF. Here I can easily spot my DXF file. I'm going to import the right section first. And this is to say if you want to offset it from the origin point as you import it. And check on the active, the imported only, and say OK. And once you import it, it's going to ask you once again if you want to check the intersection and or duplication of the imported DXF model data. Say yes. The purpose of this one is because in case there's any duplicate lines from the CAD, is to make sure all of them are disconnected and the duplicate members are gotten rid of. So those little steps that I just highlighted on, they are something that can really affect your CAD drawing import. So if you're having any difficulty importing something and encounter any issue, pay attention to your unit setting when you open the Section Property Calculator tool, and also the tolerance, and also exploding them back in the CAD program. And also over here, when you come here, make sure that you disconnect them at the interaction and also the erase duplicate member just by saying OK to initial question the program asks you. Okay, once you're in this program, as you can notice, I have 3 sections. It doesn't mean that you can draw a one single section, simple section. You can do that too. And also you can do a simple, just 2-part composite too. So basically here you can first, and also not to forget, you can start from scratch in the Section Property Calculator tool. But even my preferred way is to import the CAD. So I believe that may be the case for a majority of our attendees today too. So you can actually go to material first. Define the material first. My girder portion will be defined as C9000 concrete. Okay. Then I'm going to define my second material, which is C4500. Okay. The reason why we define the section here, material here, if it's a single part section, you don't need the material. It wouldn't affect it. But since it's multi-parts and different, they may have different material. In case they different parts have different material, you need to specify the material so that the program can actually consider the effect of the material difference when calculating the section property. Now, if you have a single section, you can go to section and generate and simply choose those parts, give it a name and apply. However, we are actually working with a composite type of section. So I'm going to go to composite section tab here and find the same function, generate, but for composite section. Okay. Name, girder. It's going to be part 1. And let me select the girder lines. Press Ctrl key to select multiple at once. Okay. Oh, total 3 parts. Okay. And apply yes. And then going to section. I'm going to first I actually let the program know this is a section that's made of 3 parts. And then you can go to the section and add parts to them now. Part 1, girder, part name. Select the lines for just the girder this time and apply. And this time select the parts for the cover plate. Give it the second part. Provide a name. Define the material for it. Apply. Say part 3, that portion, and also apply here. Yes. So this way you can make 3 different parts, specifying the material that you have. And once you do, you can actually export it. Before, one more step. So give it the material first, define the section, add parts to them, and come to the property and calculate the composite property. Mesh size, I'm just going to go with 1. But again, right now my section isn't very sophisticated. But if your case, your section has like very like an arched portion, like a curved, let's say between the web and flange, you have to reflect the curve between them. In that case, the mesh size may need to be reduced. It's actually going to indicate in the message window that the mesh is too coarse, that it needs to be the mesh size needs to be reduced. So now I'm ready to export this data. Going to name that as 3-par girder. Okay. So once you define it, you can come back to Midas Civil, go to Properties main menu where you can define material section and other related properties, and add a section over here. And depending on what type of section you're importing from the drawing, you have to go to specific portion to it. If it's just a regular section, you can go to a general section for a single part section. If it's a pre-stressed concrete section, like unique box section for your state, let's say, although you can find a lot of them in our database, you can actually go to PSC value here, and you can also import from your own section property calculator. The part that we have right now is a composite type of section, made of 3 parts, and it's actually a general type. It's not either T, PSC, or steel eye or top. So I select composite general, where I can import the section property calculator file. Press import SCC file. 1 second, let me organize better. Yes. Find the location of the file once again. Okay, and 3-par girder appears here as we defined them, exported before. And say open. Okay. Do you notice how this window has changed from nothing to this data that we created before? So this is how you can define an arbitrary section. Based on my demonstration, I believe you can actually catch how to use the section property calculator tool for a single part section or multi-part section. It's the girder number 2. Yes. And when you actually, and here you can specify for more than 2 portions. I mean, for 2-part section, it's obvious that what is the before composite section. But for like 3-part sections, it's not as clear what is the before composite section. So it's going to ask you if part 1 is by itself is the before composite section, or part 1 and part 2 combined is the before composite section. So you can manipulate those parts too. And when you actually press on the show calculation results, it's going to show you different calculation results like this. Okay. So this is how you can define your section using a CAD program and also and section property calculator. Yes, first, a few attendees, I do see your hand raised. If you have any question, please note it to the question box. I'll check the question box from time to time. Maybe if it doesn't go with the flow of the training very well, I may answer them later, but I'll try to cover them and make it relevant to your question as I see them come in. Okay, so what I'm going to do from now on, I'm going to quickly set up a straight line girder model so that I can show how to, so that I can help understanding how to use construction stage function in Midas Civil. I'm going to define 2 materials real quick, one for the girder portion and the other one for the deck portion. Girder C9000 and C9000 concrete was for the girder portion. and 4500 was for the deck portion. So I defined them in ASTM-RC material database. The reason why I defined my material before already, right? But I'm defining them once again. And for the reason for defining them twice is because the materials that I manually input in the section property calculator, it was simply for calculating the section properties. And the reason why I input the material in Midas Civil again is because this material is something that the program is actually going to use for considering, for calculating the self-weight and also the basic material. So this isn't related to calculating different parts to the section. This is the actual base material that you will need to define. I have a question come in regarding the unit setting. So in the section property calculator, when you define the material, yes, right, correct. The unit wouldn't show over here, but the thing is, so you have to make sure which unit setting has been picked when you first open the program, or when you can actually go to setting and check it. Section property calculator interface is a little less sophisticated than the basic Midas Civil, but basically you can come to tools and setting and check the unit. But as you're right, the unit will not be showing when you define them like this. But it's going to show when you define within Midas Civil. Okay. Now I'm going to define a straight line real quick. I'm going to model 120 feet long line girder. It's going to be a straight one. So first I create the beginning node and determine how many times I want to copy it and determine the distance gap between the copied nodes. So 12, I copy them 12 times and at 10 feet apart. I'm actually modeling total 10. Total 10, 13 nodes like this. And you can go to the shortcut key here and turn on the node number. All these little details, turning on the node number or changing the unit, more of a details, since this is more of an intermediate level class, those are, you can actually refer to detailed step-by-step tutorial material. But for today, during the session, let's try to focus on getting the core parts for the post-tension application. And then I come to node and element, create element, and select the material and section. When you select the material for the composite section, I define two materials, grade C9000 and C4500. But when I actually model them, I'm going to, when you model your beam elements, you can only assign one material property. One beam element cannot have two different material property, right? So you're going to specify grade C9000 as the base material, which is the girder material, and pick the section, and then click on the nodal connectivity and draw a line like this. So this way, when I turn off the hidden view, it's a simple line. When I turn on the hidden view, you can see the section properties, section dimension like this. Okay. I'm going to define my boundary too. Coming to the boundary main menu, define support real quick. Okay, actually. Okay, and then I'm just going to define self-weight for this example. Okay, so I define my self-weight load case, and also I define my self-weight by defining the factor to the gravitation. So self-weight is calculated automatically using the section and material property in Midas Civil. So we have the basic materials ready to set up the construction stage. This is actually the key portion for understanding the construction stage. So basically, when you define the construction stage, you have to go to the load main menu, find the construction stage load type, and click on define CS. And when you click on add, you can actually define multiple stages. Stage non-composite. Duration will be just about, let's say, seven days. And then we don't have any groups yet, but let's define the stages first. And then composite, plate, covered, and then full composite. So I define 3 stages, 1 non-composite, plate covered, and full composite. And here what we need to do is we have to go to the group tab, and then specify the structure group, boundary group, and load group. When you click on define construction stage, notice that we need to have a bunch of groups: element group, boundary group, and load group. And notice structure group, boundary group, and load group. And structure group right here is actually the same thing as the element group here. Just a terminology switch. Coming to the structure group, so basically, one second, let me go back once again. So basically, how the construction stage works in Midas, if you, for today's PT, it's a post-tension box girder training. So I believe majority of our clients do have an experience with FEA program. So basically, it's similar, but you need to actually provide a group for the node and element, and group of support, spring, elastic link, those type of boundary component, and also groups for the loadings. And how you actually bring different part into different stage, it's a matter of activating different group in the proper stage that you want in order to simulate it. Okay, so I'm going to make one structure group, girder line 1. So, and then for this case, I'm going to select every element and assign this structure group by just dragging and dropping. And same goes for the boundary. Simply, it's just a support boundary. So I'm going to drag and drop too. And then for the boundary, since there are multiple type of boundary things, it's going to ask you how you want to, which component do you want to include into this boundary group. But basically, if you didn't know that you can actually use the drag and drop feature to assign different group, here you go. And also for the loading group, self-weight. And for this loading, I have to go back to the load. I have a second stream menu open. You can do that by right-clicking here on the toolbar and click on the stream menu number 2. And also when you go to the tools, you can customize by opening the second stream menu like this. Coming to the group, the work stream. So here I'm going to go into the properties. So basically you can see a summary of all the data in the work stream. This function dialog box opens up by default on the left side. And right now the load group is default. So I'm going to change it to the self-weight and modify. Okay. So girder line 1, support, and the self-weight. And how do you check later on if the things are assigned to the right group, right? So let's say for the support, we want to make sure that my supports are assigned to the support group. then you can go to the worksheet, find the boundaries and find the support, right click and get to the tables. Then at the end of the table, you can see the group column. And it's going to tell you which boundary group these two supports belong to. Okay. So what I'm gonna do, I'm going to assign them into the first stage. Girder line, so non-composite in the first stage, stage 1, non-composite, the girder line will be activated. Yes. And again, for the boundary, support will be activated at the same time. And the loading self-weight will be initiated the first time too. Okay, so what happens now when you, with the construction stage window, when you actually go through each stage, you're gonna see in the non-composite state, all of the element, boundary group, and load is activated. And nothing has been added to the plate covered and full composite, so there's no change in different stage. But this is not what we want, right? We actually need to separate these parts. In order to do that, you can go to the load, stay in the construction stage load type, and find composite section for CS. Click on composite section for CS, and what the purpose of this function is to separate the parts, like the composite parts. So these composite parts, 3 different parts, it's assigned to individual beams as a single section property. So in order to separate it, so usually what you have to do is you have to model the deck as a separate beam member or plate member, but in Midas you can model them all together. But you can actually separate them using the composite section for construction stage. Add, and then active stage will be non-composite since that's when the girder is activated. And for the section, I'm going to choose 3-part girder number 2, which is the section that I want to, deal about. And it's going to be a user-defined type of section or general, wouldn't really matter. And for part 1, the material type can be either element or material, and you can pick the girder material. And let me come back what is the material and element once again, but give me 1 second. Let me first choose the material for different parts. So this part 1, 2, 3 is referring to girder, cover plate, and the deck portion 1 by 1. And the material type, again, remember in an FEA program, only one single material can be assigned to to individual beams. There's no such thing that you can assign 2 different materials to a single beam, right? Element. So in order to reflect different parts, what we do is we actually bring this function so that we can actually apply different material for different parts. Not as the element, but using our composite section type. So part 2 has different material. It's got C4500 concrete. So for the part 1, I have C9000 concrete, and part 2 and 3, I have 4500, right? And what I meant by you can for the girder, which has the base material, you can actually pick element. And what this means is that remember we assigned the girder material to these individual beams. We didn't assign 4500. We actually assigned C9000 as the material for this element. And when you choose element as the material type, it's going to bring that material by default as the material property for the part 1. So that's the difference between the material and the element. It's for your convenience to kind of leave the material as the element and stay with what you define on the basic, the global model. Composite stage, so this is where you specify at which stage you want different parts to be activated at. So part 1, the girder, we want to activate it in non-composite, right? Which is already our active stage. Active stage, non-composite here. Pay attention to active stage, the same terminology. It means that this girder part 1 will be activated and the active stage chosen as the basis. Part 2 will be activated in the plate covered stage, the second stage I defined, and part 3 will be activated in the full composite section that I defined. Okay, so this portion right here is to let the program know at which different stage you want to activate different portions. And in age, so age is related to the time-dependent property. So basically, I will come back to this part shortly in a little bit, but just notice that this is for in connection to the time-dependent property of the material. For this simple example for the first part, I'm not going to use the time-dependent material, so I'm going to skip the age. Age is actually related to the creep and shrinkage calculation. I'll come back to this portion too. One second. So I wasn't able to register the data, and the error message is telling me, I hope you can see it. Oh. I hope you can see. So basically, it was telling me that I'm currently in a construction stage, and this information cannot be defined in a construction stage. It needs to be defined in base stage only, was what I was trying to say. So go back to base. Let me real quick define that composite section data. Okay, so now when you review your non-composite state, it's not going to be the same anymore. Before, it was like this for all 3 stages, but now it's actually separated into non-composite, plate covered, and full composite. And let's run the analysis. Okay. You can go to the result, find, let's say, displacement, and choose different stage, and see different stage output. Non-composite, right now we are looking at the deformed shape. Don't be overwhelmed with the deformed shape. It's actually scaled, so if you want, you can review the real displacement with the scale off. And plate covered and full composite. So that was about how to distinguish multiple sections. Moving on to the second portion. Okay. Moving on to the second portion, tendon and construction stage. And I had a question saying, can the error message be displayed before you say OK? Unfortunately, it's not going to let you know prior to saying OK. Okay, and as one of the question was raised, it's correct. H is only for CBFIP, right? So when you use the ASHTO, it's going to be a little different. Let me mention that part in a little bit in this second portion. Tendon and construction stage, geometry generation from DXF or section assignment, boundary, tendon layout, and setting up the construction stage, and construction stage analysis and results. So for the cross-section, we already reviewed the cross-section, but this is an overview of the structure. And this is how the tendons will be located. It's a spliced structure, as you can see. Staging will be in 4 different phases. Temporary support first, then the girders, and then pre-stressing. Construction stage, as you can see, this will be how it's going to be composed. We have detailed training material. So step-by-step tutorial manual. So for the time being, what I'm gonna do, I'm going to have a fully model open and actually go over each aspect one by one. So that way we can get into more detail with the time given. So basically in the stage 1, the girders are activated, and the abutment portion has a link, and the beam and release is applied for the temporary support at the temporary support. For the loading, just the self-weight is activated. In the stage 2, the cover plate for the support region is activated. And in stage 3, the post-tensioning occurs. And in stage 5, the dummy deck is, so basically the deck portion is activated. And the beam and release is applied at the temporary support. And, yep. Okay. Let me refresh my view 1 second. So this one, there will be 2 ways to model this structure. One, you can actually, for the basic layout, you can actually use our node and element to create the node and rotate it. Again, you can refer to more detail in the step-by-step tutorial manual, which will be uploaded on our website and sent out to everyone here today. So things to go over is time-dependent material and the construction stage setup and the stressing. One by one, let's come to material and time-dependent material first. So when you come to the properties, you're going to find the time-dependent material section. And here you can see the creep shrinkage and compressive strength, the part that we are interested in. Here I already defined let me change my unit setting real quick. So this is the function for creep and shrinkage. You can go to creep shrinkage here and define neurally. Let's review what I have so far. So I used CVFIP as mentioned, and here you define the notational size of member. But as you know, we have 3 different parts, and this will be different for each part. So that was the purpose of the H column in the construction stage 4 composite stage. And as mentioned, as per ASHTO, you input your volume surface ratio separately. So depending on which code you want to go with for defining your time dependency, it's going to change your input parameters. And also our CVFIP database will be updated shortly, pretty soon, before the end of August. It's going to have CVFIP 2010 edition. So basically, based on these input parameters, the program will draw the function. You can also use your draw them too. And I also defined one for grade C4500. And when you come to the compressive strength, same goes. Depending on the code that you choose, you can actually specify, actually draw the graph like this. And volume surface ratio are not actually, I'm answering one of the questions raised. Volume surface ratio will not be updated automatically as you change your section. So time-dependent material is, so you can define them very easily. It kind of went too quick even, because you can actually define them based on the function that's already embedded. And you can define them based on just the simple input parameters the program asks you. You don't need to write out a time-dependent function or anything. It's going to be there. So you can simply input the basic parameters and have the program verify the function for you. And if you need to, of course, validate those functions, you can check it with in the tabular format and also the graphical format. Once you are done defining your creep shrinkage and compressive strength, you need to link it to the materials that you have. So just because you defined a function for compressive strength or creep and shrinkage, it doesn't mean the program knows automatically which one's what, It's something that the users need to link. So we have to, after defining creep shrinkage and compressive strength, we just go through one more step to link each portion. Choose the one from the creep shrinkage, choose the proper compressive strength, and select the section, the material that you want to link these creep shrinkage compressive function, and say add and modify. Same goes for the second material, just change your function. Choose different material, say add and modify, right? Okay. So this is how you have the time-dependent function run. And how it's going to work, simultaneously with the construction stage analysis setup. So because, we define our function, but it's one function, how does the program know when is the girder activated and at what point of the time dependency is the function at, like what is going on, how are they working all together? So basically you assign a function to the material, right? So we have two different materials linked, grade C9000 and 4500, right? We have different time-dependent functions. And when you go to define your construction stage, what you're going to see is the age here. So right before that, just hold on to it for just a little bit. Let's go over how the construction stage is formed for this structure. In stage 1, same as before, the girders are activated, as you can see, and also what we saw in the PowerPoint. Stage 2, the top plate is just put on for the support regions. And I forgot to mention this portion, but we have the temporary support like this at the splice locations. Plate is covered, and in stage 3, the temporary support is removed. And here some of the other, the pre-stress loading is activated. And in stage 4, the deck is poured. And stage 5 is actually for considering the long-term creep and shrinkage. So the girder portion that has the grade C9000 material, it's already started in stage 1. And in stage 2, the plate cover comes in. And in stage 4, the concrete is poured and hardened activated. Keep that in mind. Come back to our input interface. Pay attention to stage 1, construction stage 1. And here, the girder group is activated in the first construction stage with age of 7. And in construction stage 2, plate cover comes in, but that's handled in the composite section for construction stage. And same goes for the rest. But basically, keep in mind the girder is activated with age of 7, right? And when you come back to the loading and go to composite section for CS, find the list of different composite section for construction stage defined. And pay attention to the age portion again. And here for age, oh, actually, that age, not the volume surface ratio, but then age for CBFIP, they can be automatically updated when you change your section property. And I forgot this portion, but you can actually say use this function here, update all age. So if you don't want to update for each different section, you don't want to calculate for different section. We defined the section already, so why not have the program do it for us, right? So use this function to update all the age. And age right here, so this is relevant to the time dependency of the concrete once again. And each time dependency of the concrete starts when that element is activated. So in the first stage, the girder is activated, meaning the first girder portion is activated with grade C9000 material, right? With age of 7. What this means is it's going to be activated with age of 7, so that at the if you look at the compressive strength, it's going to have the strength at age of 7 days. Same goes for the part 2, age 7. So when this element, when the plate cover is activated, it has the strength at age of 7 days. Same goes for the deck. And the reason why we don't really set it to 0, in reality, we pour the concrete and it doesn't have any age, especially for the deck portion. But we still set the age to be, you need to give it some number such as 537, some small number. The reason for that is because it's actually a function how we can consider the compressive strength, right? So if you put the age as 0, what's going to happen is it's not going to be able to do the nonlinear computation here. It's going to get stuck in the 0 infinite loop. So you have to give it certain age, so that way the program has a certain strength value to pick up from, and actually continues on with the rest of the function. So that's why giving it the age of, let's say, 1, 3, or even like 5 and 7, those arbitrary number that just to give the program certain number to start with for the function, we provide an age. And also age, not just for those purpose, but it's critical to reflect, let's say, freshly poured concrete cast in place or precasted members. So that's how you can distinguish precast members and pour in cast members. So if the age is about 28, that means yes, correct. So I had a question asking what age is recommended to capture the effect of initial shrinkage. Actually, for shrinkage, it wouldn't matter. Shrinkage, initial shrinkage. Actually, I'll get back to this portion. Before the compressive strength, if you want to reflect the precast type, you can give it age of 28, letting the members start with the strength of at 28 days. If it's a cast in place, you want to give it some beginning day number like 1, 3, 5, and so on. Just a number to give the program something to start with. So when in the first stage, the girder is activated. So this girder currently has, in the very beginning, has the strength at 7 days. And in stage 2, as soon as the second stage starts, this plate cover also has the strength at 7 days. So that's how the time dependence functions and the construction stage analysis work simultaneously. And the last portion is the tendon property function. So tendon definition is made into 2 different parts. One is for 3, tendon property, tendon profile, and tendon pre-stress. When you come to the load main menu, come to the temperature pre-stress loading type, and find the pre-stress loadings. Tendon property, profile, and tendon pre-stress. So tendon property basically is you define literally the type of the tendon. Is it a post-tension, pre-tension, or external? Choose what type of material you're using. What is the total tendon area? You can also choose based on the strand diameter and also the number of the strands. What is the duct diameter? Relaxation coefficient. What is the code that you want to use for calculating the relaxation coefficient? And then rest of the input for calculating the loss stress. And basically, this is why working with either pre-tension or post-tension type is flexible. Combination of it or just one or the other, you just need to define the proper tendon property. And you can define multiple tendon property too. It's just a matter of which property you link different group of tendon profiles. So second portion is the tendon profile. Tendon profile can be defined in manual way using this type of coordinates, but it's very it's doable. But if you do not want to do it this way, looking for a solution in which the program optimized it better, you can go to the structure, go to pre-stressed concrete bridge, and find tendon template. And here, choose the group of element you want to assign. Let me do that real quick. Oh, it needs to be the regular section. But basically, you can actually choose from different tendon type. So this way, you don't have to work with the coordinate number. All you need to do is simply define the distance from the top, bottom, and also the distance from the end to the curve point. And you can define it for span by span or for different spliced parts. You can actually define for the entire line depending on how you select this. So if you only select, let's say, one splice portion, you can define the Girder tendon for that area. If you define all the element, you can actually define this hard curve, whatever the case be, for the entire area too. So this is maybe an easier way for you to deal with. You can also adjust how many spans you're gonna have and so on. So this way, yes, it's easier to work with. So if you don't want to work with the coordinate number, there you go. And then the last portion is tendon pre-stress. So in this tendon pre-stress is where you define the number, the actual stress number checking force. So we have all different tendon profile, right? So choose the tendon profile and choose the, type in the stress tendon stressing force, checking force. And then let the program know if you want to check it in the beginning end or the end or both ends. You can choose either to input stress or force value, and then also you can define when you want to grout it if it's an unbonded type, and edit. And when you define the tendon profile, you actually have a choice to select the tendon property. So remember I mentioned that you can define multiple tendon properties. If you're working with a post-tension, you can define post-tension. But if it's a post-tension but different type, if the property isn't really the same, which may be the case often, you can define multiple tendon properties and just pick the proper tendon property when you define the tendon profile. So as mentioned before, it's not really a matter of is the program capable of doing one or the other. You can actually handle all of them within one model and one program. And it's just a matter of linking which tendon property, post-tension, pre-tension, external, with the specific tendon profile you want to assign different property for. And then assigning when to stress it. And also, how do you know when to apply the stress and things like that? So when we define this tendon pre-stress load, you can also define the load group name. And load group. Does this sound more familiar now? So basically, you assign each pre-stress into a load group. They don't have to be assigned to different individual groups. You can actually define them in different groups depending on when you want to activate them. So remember, when you compose the construction stage in the loading tab, you can notice the post tension is actually put in the third stage, as in order to make it in connection to the actual project phase, staging phase. So this load group post tension is activated in the third stage. And let me go back to the tendon profile portion. Let me cover them a little briefly. So, okay, I'll go over this interface. So you can specify the tendon name. Basically, remember, you can actually choose the type, herb or curve in the structure main menu. When you do it, it's going to create this type of individual coordinate data. And also you can, from the scratch, just define the data with the coordinate too. And here, tendon property, choose the tendon property and choose the assigned element. This tendon line is assigned to the exterior girder. So how do I know? It has the assigned element to 216, 167 by 3. So let's say if I actually choose this element, it's going to be updated here. And then you can choose your input type to be either 2D or 3D. If you choose 2D, you're going to be defining X, Y first, and then Y and Z as the second. If you do 3D, you define all three X, Y, Z coordinate at the same time. And straight length of tendon, how long is it, goes for, and curve type, is it spline or round? This is to actually for shaping this type of curves. I actually barely see a case where the round is a better type. And typical tendon, this can be pretty useful if you're working in a preliminary stage. So basically, if you don't want to define all your tendons, in the very beginning phase, what you can do is you can define one coordinate at the bottom of the girder, or you can, define one more for the web portion and another one for the other side of the web. And what you can do is you can actually just increase the number of tendons. So with one typical profile, just increase the number so that the program can actually consider 5 times of the effect of a single tendon. So that way, if you're not really set with your tendon data yet, you can actually do basic tests, like approximate test with this typical tendon function. And the tendon length, you can either use and define or have it auto-calculated. And I mean the transfer length. And the profile, this is actually something really useful in our program. So you can actually define your profile to be a straight line. So define the coordinate and just have it straight, right? And just define which one is your insertion point. Profile, insertion point, right here. Second option is curve. So basically, you define about the curve that you want to draw, define right over here, the coordinate. So profile, insertion point, once again, pick a point. And radius center, what is the center of the radius? Maybe somewhere here for this structure. And the offset too. How much do you want to offset? And so, but then I hate both options. What I like to go over and what a lot of our engineers, user engineers actually conventionally use more often is the element type. So element, basically, it runs based on the assigned element. So this coordinate value will be about the element that you select. So right now I select this exterior girder, right? So this is my reference line. If you choose straight, just the insertion point, that's your starting point, and then it goes by the coordinate. If you choose the circle too, you draw your insertion point in the center of the radius, and about that circle that's already defined over here, it kind of offsets using XYZ number. Element, you just need to choose a group of element and define the offset locations. Yes, X is the longitudinal, Z is literally the vertical, and Y is the transverse, correct? Yes. And this is what really makes it easy for a curved, like irregular type of structure too. One minor difference between the curve and element is when you actually draw the element, what happens is element itself is straight. As mentioned in the beginning, in FEA program, elements cannot be curved. That's not a proper type of component in 3D FEA program. So every single element is straight. So when you actually have the reference axis as a element type, what's gonna happen is these little components, it's going to draw the coordinate. Do you see this orange line over here? Not the red line, but then the thin orange line. So that's the tendon profile. As you can see, it's smooth and curved. But if you actually go into the reality, like the bottom point, it's actually straight because the elements are straight too. So if you were to look for like differences between the curve type and the element type, because it's about based on the elements, the tendon also is it's actually straight when you look into the base segment. When you do the curve though, it's actually drawing a curve line. So if it's very curve critical, curve may be more accurate, but based on my experiment and based on my clients' feedback too, anyone who used it in the past, element and curve didn't really have much difference. But it's actually the same for the girder too. It's a curved structure, and we modeled it with a group of straight beams. And the reason why we segment it like this is to reflect the curvature properly. So same goes for the tendon. If you really need to be accurate, you can go for the curve. But from the cases, not much difference between curve and element. But that was the difference between the two. And this one is to here. This is to let the program know which point is the insertion point, the starting point. Is it the element over here or is it the element in the other end? The program wouldn't know unless you tell that number 2. So that's what this is for. And if you want to copy, you can copy and move. For copying, you can actually choose, let's say you can copy in different way. You can actually copy with element increment. So, and also if you want to copy at equal distance, that works too if it's a uniform structure. If you want to, let's say, assign this tendon into this tendon, right? The inner one this time. You can actually choose different group too, but you know, they don't have the same length. For that, we actually have an option to auto adjust the tendon length here. So this way, even if the point isn't really the same, I mean, even if the length isn't the same due to the curve or skew, whatever the case be, it's actually going to take that into the consideration and reduce the size or increase the length and so on. So I actually didn't input all this manually. I just create one and copy them through, just manipulating information little by little. But that's where the copy and move can be more useful. And also, we really pay attention to the CAD and the program communicability. So you can also export this to CAD DXF. Or the other way around, you can go to the tools, use the tendon generator. And actually, if you actually drew that in a CAD program, you can actually import the DXF and yeah, work with instead of working with the coordinate, you can define the profile with the DXF file. Okay, So simultaneously, pay attention to the workstream menu. Let me shrink it. 1 second. Let me just open up material, not material, tendon profile and the support. Okay. And when we go over stage once again, girder activated with the temporary support. And in stage 2, the top plate is covered with the compressive strength at age 7. Part 3, it's actually pre-stressed like this. You notice the PT, the post-tension load, is activated in the static load here. And in stage 4, the deck portion is fully activated, meaning it has the full strength now. Stage 5 is just 10,000 days to consider the full shrinkage and creep effects. Okay. So when you review the result too, you can review the result at each different stage. Let me actually draw deflection contour. Stage 1. It's an exaggerated view, so when I turn on the real displacement, it's not as drastic. 2, 3, 4. You can review stage by stage. The last portion will be the staging, not much of it anymore, but more on the live load portion. So for this one, I'm going to define 2 lanes running on top of each girder, but it doesn't mean that the live load can run in the middle. It can also run at any part of the bridge. But for this one, I'm going to define 2 lanes like this, and just the design truck and tendon truck. This portion will be very short, and after that, we'll be moving on to Q&A session and closing. So moving load also, more details about like different cases, for flared or unique structure, it will be covered in our moving load session. But today, for the moving load, you can actually define in 3 steps. Define your lane, vehicle, and moving load. And for this one, since this is a structure with beam element, I define line lanes. As mentioned before, I had defined 2 different lanes, lane 1 and lane 2. So how is the lane working? So to give you the basics about our moving load is based on influence line analysis. It's not based on the distribution factor analysis, but you can actually do a workaround to reflect that by defining a single line girder. Just take out a line, do a line girder analysis, and do the distribution, calculate the distribution factor outside of program and input in the program. But for this type of complex structure, it's not really the case. So the basis for the moving load in Midas is influence analysis. And right now, you have to define the approximate location of the lane and define the vehicle loading and moving load. And also, according to in order to meet the AASHTO, the dual truck rule about the negative moment at the support, you can define the lane support negative moment and lane support reaction. And actually, to provide a news for the update for the moving load, so our moving load history was first, what I told you up to now was what we had for quite a while. And as an improvement to our moving load, we actually added this portion, traffic lane optimization. What this is about is, let me take to online help manual. You can open the same manual by pressing F1 key. So our first improvement to our moving load analysis was to, you can actually approximate the location of the lane and have the program floated at the middle and the end and the other ends. So that's how the, that's a little more detail the moving load analysis covered right now. And so you can basically specify the lane width. And let me change my unit to feet. Give me 1 second. So activate it, change your lane to, let's say, 10. And then you define your wheel spacing. The reason I give it 10 is because in order to leave out the 2 feet at the end, to leave the end clearance, 2 feet end clearance. And this is how it is. You have to give it approximate location of the lane, moving load. But our second improvement to the moving load analysis that will be changed in December release. It's going to be you don't have to define the approximate location even. You just give the program the width of the lane, the vehicle wheel spacing, and just give it the loading type. And the program will be actually doing just the all full floating in the transverse direction too. Currently, it does it for the longitudinal direction, but it's going to be doing that for the transverse direction. But that's the second improvement that will be joined in December. But this one, it goes the same. You choose your basically, when you define your lane, give it a name. If you want to do approximation, just turn on this option, tell it the wheel spacing and the lane width, and the eccentricity is about how off you want to define it from the reference line you picked. And the reference line, you can pick it based on this number, the element number. So lane width, wheel spacing, and traffic lane optimization will actually refine the location of the lane. And vehicular load distribution, so in Midas, you can define the lane load distribution. So the lane element isn't really recommended unless it's a single box type of structure. You can also refer to more detail in the online help manual too, but basically, what's going to happen is if you choose the lane element, it's actually going to define, let's say, location of the wheel like here, and then it's going to apply the moving load, the axial force and the moment about that reference line. But when you actually choose the crossbeam type, what's going to happen is this is more of a natural way. So it's going to use the crossbeams to actually distribute the force to the girders. But if you go with the lane element type, it's going to apply those with the eccentricity about the reference lines. And lane element isn't really recommended unless it's a single girder type. And crossbeam is the type you want to go with for any multi-line girder structure. So here I choose crossbeam type and select the crossbeam group as the dummy deck. So dummy deck is this transverse elements without any weight, but just the stiffness in order to reflect the concrete stiffness in the transverse direction. And here we go. Yep. And one more detail. If you want to reflect the dual truck rule according to AASHTO, you need to specify the location of the span. So right now our element is, 1 second. So this is our reference line, right? Reference line for the lane. And we have to let the program know which location is the start of the span. So that way the program can consider, it can consider the dual truck roll. I mean, know exactly where is the support located. It's an FEA program, so it needs a little more additional information like that. So check on element 45. Element 49. Moving on, past the temporary support here. 97. And so on. So this way, let the program know which location exactly is the support location so that the dual truck roll can be considered fully. And when you review your moving load analysis, you can actually review the envelope result too. So when you go to results, force result diagram, you can review with the bending diagram format or even stress, whatever the case be. You see all the combination here. See the moving load. Find the moving load defined. And all means it's an envelope case. And if you go with MV max, it's to review just the positive moment. MV min, so min max, all is the envelope. Min is just the minimum, like the negative values, maximum negative value. And all will be the envelope of all. And this is the envelope result. But if you're looking more for the forces, the concurrent forces, so this is a normal force. These are actually the values, that's the maximum, the worst case at every location. But if you're more interested in knowing the concurrent forces, find the location of your interest. Element, it's according to the legend, it's telling me the element 83 is where the maximum positive moment occurs. So 83 keep in mind, and element 50 is where the maximum negative moment occurs. So looking at your envelope diagram and the legend summary, you actually get to know at which location you want to extract the concurrent force from. I mean, it wouldn't really make sense to extract like a concurrent force when this member is undergoing the worst case scenario, right? You want to extract the concurrent force for the worst cases. So keep that in mind, element 83. Go to moving load tracer, find beam force moment and 83, and say OK. So this way, you can find out exact location of the vehicle and the lane load when element 83 was undergoing the maximum moment. Okay. And regardless, if you're wondering about, like concurrent forces when reaction was the worst, you can find them all. Go to moving load tracer, find reaction displacement, truss force, beam force moment. And for the beam force moment, you can not only do that for the bending moment, you can also do it for shear. But most likely, we are interested in taking the moment and also for the reaction. So about different case of concurrent forces, you can use a moving load tracer like this and find out when specific location is undergoing the maximum force, what is the scenario with the vehicle loading. Let's say over here, where is the vehicle located with this is undergoing the maximum bending moment. So those type of information can be extracted using this moving load tracer. Okay. And one last portion will be approximate tendon loss. So if you actually run the analysis like this, I didn't cover too much of the pre-stress, the results, but then basically any type of pre-stress or creep shrinkage data, You can review in the diagram format, or you can review in the table format too. Remember force, bending diagram here? This is the same location you came to extract the result about dead load or just regular construction load, right? But when you come to here, you're gonna see the construction stage loadings are categorized into dead load, tendon primary, secondary, creep shrink secondary, shrinkage secondary, and summation of all, creep primary, shrinkage primary, one by one. And this type of segmentation, the program does it automatically. So the tendon loading, the program can obviously know which one's the tendon data. Creep, it's calculated based on the material and the surrounding component, not exactly the loading. The program knows and extracts creep and shrinkage, secondary, primary result at different category. So this is something that the program does automatically for the construction stage. And if you want to break down the dead load, you can actually go to analysis and go to construction stage for that and segment your dead load. Right now, anything that's not a part of tendon, creep, or shrinkage goes to the dead load. Okay. And I have a question come in regarding the moving load portion, but I'll get to it in a little later. So basically, the tendon pre-stress result 2, you can review just the same way you review for the regular force and so on. And if you're looking for more of a tendon-specific results, tendon location coordinate at different stage, meaning how is it moving, getting slipped, and tendon elongation, arrangement, or tendon loss, or tendon assignment loss, this type of the stress-related data can be found from this tendon-specific result tables. And as you can see from the top, these are the type of results that you can get. All the detail on the stress and the loss results. At different stage, about each cord, each tendon line, and so on, all that. In stage 1, it's not activated, so the values are 0. Okay. And how do you know, let's say, how do you know, like, where is this occurring? It says element 55I, like, where is this? You go to the model view, use the window here, type in 53. It's going to highlight it. And also go to query node or element, find where exactly that location is located. Or if you want to go extract the mass data, you can go to the work tree, actually get to the table of the element or the node. So this way you get to know the exact coordinate location of the node and element. So the result will be presented about the node and element, right? So about each node and element, you get to know exact coordinate